Hi everybody, in this video we are going to talk about the first controlled polymerization technique, and the name of it is the ATRP, atom transfer radical polymerization. Well, if you remember, when we were talking about the free radical polymerization, here we mentioned that the propagation step is a first order reaction and it is directly related to the concentration of the radicals which are present in our sample, okay, that we are doing the polymerization. But for the termination effect, you see here that two radicals are going to contribute. So if we try to decrease the concentration of the radicals which are present in our system, we will lead to the more decrease into the termination step, because it's a second order reaction, because there two radicals are going to contribute for the termination here. So what we are going to do is to decrease this step, the kinetics of the termination effect, as much as possible in order to make sure that the propagation is going to occur in a more controlled way, okay? And if you remember in the video of the free radical polymerization that you watched here, by increasing the temperature, when the initiator is going to divide into two parts, it will go for attacking the monomers that we have in the system. And you see here, once it is attached to the first monomer, the available radical on the other part of the monomer is always ready to propagate and is always ready to attack the other monomer that we have here to go for the propagation. And the problem is that because it is available, if we have at the same time another chain like that and they two meet each other, so the termination will occur. So what we are going to do is to decrease the availability of this radical here in order to lead into a more controlled polymerization process. And here you see what we are going to do by the help of the atom transfer radical polymerization. Well, but the idea behind that is to use a halogen which is connected at the end of our polymer chain. Okay, you see here the halogen is connected to the end, just like what we have here. Just imagine here a halogen that is connected. So this is the one that is going to control the polymerization process. So this halogen has affinity towards the transition metal. You know, here we have the copper, it can be, you know, some other metals as well. And you see that when this halogen is detached and is connected to the metal that we have here, there will be a radical present for the propagation in order to connect to the other monomers that are available. And what is this? This is called complexing ligand that contains the copper inside it. You know, it is useful for solubilizing the copper and this agent into the organic solvent that we are going to have our polymerization process in. Depending on the type of solvent, we can change this complexing ligand to perform the polymerization reaction in different solvents. And you see here that the basic idea, this clever idea of detaching the halogen at the end of the polymer chain to let the polymerization progress continue, will help us to control the polymerization reaction. And this is what you see here. We have the polymer chain which is connected to a halogen, and we have the transition metal which is solubilized by the help of the complexing ligand. So let me show you again. This is the metal and the complexing ligand that we had here, the metal and the complexing ligand, and here the polymer chain and the halogen, as you see here, the polymer chain and the halogen. But the fact is that the reaction constant at this way is smaller compared to this way, to the reversible one. You know, this reaction is occurring at the equilibrium state, and it says that once this halogen is detached and goes here, you see here the halogen is detached and goes here, and we have so it's happening at the equilibrium state, and the constant rate for the reaction to occur in the opposite way is larger compared to the reaction occurring in this way. And it tells us that because this constant is smaller, so the availability of the radicals for the polymerization and for the propagation will be decreased, okay, because this constant is smaller compared to the reversible one. And because the propagation is a second order reaction, as I showed you here, is a second order reaction, it is affected more compared to the propagation reaction, which is a first order. So it has the power of 2, so the propagation will occur much less the termination will occur much less compared to the propagation one. So it was all about the atom transfer radical polymerization that we have, and just remember that we are going to decrease the availability of the radicals in our system in order to decrease the termination, because the termination is going to lead to a broad molecular weight distribution. And you see here that we can change the let's say the halogen that is going to detach and the other properties of our initiator in order to control the reaction rate. You see here that we can change from chlorine to bromine and iodine, and also the degree of initiator and the radical stabilizing groups can differ, and we can based on that just vary and change the reaction rate. Well, and also here you see the different complexing ligands which are available for the ATRP, and I told you that based on the different complexing ligand we will be able to perform the polymerization in different organic solvents. And in this slide you just see the wide variety of tools available for the scientists in the field of nanomedicine and chemistry to work with in order to just do the ATRP for the synthesizing of polymeric particles. And you see here that at the end of our polymeric chain we have the halogen connected to that. Well, now these are some examples from the literature. You see the synthesis of the glycerol monomethacrylate and also the hydroxypropyl methacrylate. These two are of the most useful and most common polymers which are used in the field of nanomedicine. But here is the more important slide. If you remember, I told you about the kinetics of the living polymerization techniques, and I told you that with respect to the time, the amount of monomers which are going to be consumed, the natural logarithm of that, is going to be the same rate, is going to occur at the same rate. And you see here that by varying different solvents, they finally reach into the appropriate condition for doing the ATRP polymerization. And you see here that the second feature of the living polymerization that we talked about was the number average of the molecular weight of the polymer chains which are formed. And you see that in the number average of the molecular weight with respect to the percentage of the conversion is also varying linearly. Well, this was all about the atom transfer radical polymerization, the ATRP, and in the next video we will go for the reversible addition fragmentation chain transfer polymerization, named as RAFT. And this is another controlled polymerization technique that we will cover in the next video.